This is 1:30. Any questions before we get started?
Yeah, just a quick question on the homework. So last week there were questions spanning across all 3 lectures, but on the second homework there's only 4 questions on 4 and 5, right?
Right.
At least labeling wise. Okay, thank you.
Right. That's good enough. I think I can wait for lecture 6 for the next homework. So today I'm going to start on constitutive relations, which is a very interesting topic. I guess we learned from Maxwell's equations that, wait a minute, where did it go? Okay, it comes back. Okay, we learned from Maxwell's equations that we need only to solve 2 of the 4 Maxwell's equations. That is Faraday's law and then Ampere's law. We say that the other 2 are derivable from these 2. So we don't have to solve the other 2. But then we look at these 2 equations. They are 2 equations with 4 unknowns or 4 vector unknowns. The vector unknowns are this, and 2 equations and 4 vector unknowns are not sufficient to solve for all the unknowns that we have. So we have to have constitutive relations in addition to Maxwell's equations. We say that for vacuum, we can have this, and then D is epsilon naught of E. And if we add the 2 more equations, then we will have 4 equations and 4 unknowns. We can solve all of them. But today we're going to do a little bit more. That the constitutive relations that we have introduced, they're not sufficient to describe many different kinds of media. To be more complete, we have to say that the electric flux is the electric flux coming from the vacuum plus a term that comes from the material. This is the vacuum contribution. This is the materials contributions. Okay, because what we have is that this D is very important because partial D, partial T give rise to displacement current. Okay, and hence D is extremely important. And we will study a little bit more on P, the P's contribution to D, the electric flux. Okay. So let's assume that what is P? P is actually due to very, very small dipole densities, because when you have a molecule, and if you apply an electric field, that molecule is going to be polarized. Like the positive charge is going to go there, the negative charge is going to go there. And molecules becomes little dipoles. And you can think of that media is actually consisting of a lot of dipoles aligning themselves. And when the electric field is pointing in that direction, all these dipoles will align themselves in that direction. And they can give rise to what is called the polarization density or the polarization current. Okay, P is the polarization density. And then when you put the P into the displacement current, there's going to be additional term that is contribution to the displacement current. This is called the polarization current. Okay, and this polarization current is quite interesting, and we'll study more of it later. But let's begin with a linear medium, or just linear media, where these dipole densities are linearly proportional to the applied electric field. Let's call this chi naught. Okay, so if the applied field this is the polarization density. And then it's nothing but the density of little dipoles. Okay. And let me go to the, let me turn on this autosave. Don't have to worry about it. Okay. Okay, now autosave is on. So let's look at the second slide. So imagine that we have these molecules. Okay, these are all molecules or atoms. And they become little dipoles when you apply an electric field. Okay. And these dipoles together give rise to a dipole density, which is called P. And the formula is given by, this is called chi. Okay, this is pronounced chi in Greek letter. Okay. So let's assume that we have a linear medium so that P and E are linearly proportional to each other. We can think of this little dipoles as having electric field that looks like this. So you can think of them as looking very much like capacitors. Okay, they're connected to each other by capacitor. So you can think of little dipoles when they are aligned with respect to each other. Electric field couples the positive charges to the negative charges. Say if you have positive charge on this plate and then there's current flowing here. And then currents can flow through space very much for the same reason that currents can flow through a capacitor. AC current, I think we learned from undergraduate courses that if you have an AC current in a wire connected by capacitors, currents can flow due to the charging and discharging of the capacitors. Similarly, you can think of these dipoles as forming capacitors lined up in space, and you can charge and discharge those capacitors, causing a kind of a displacement current to flow. And the displacement current then is given by something that looks like this. Okay, this P will contribute to more displacement current. Okay, so one thing to notice is that we're going to study this relationship mainly in the frequency domain. In the frequency domain, it's very easy that this will be a function of frequency. Epsilon naught is a constant, but chi usually is a function of frequency. So in the frequency domain, we can say that the polarization current is related to the electric field in this manner, or the polarization density is related to the electric field in this manner. And for all of us who have studied electrical engineering before, we can translate this. This could be a function of R2. Okay, this can be a function of R. And then we can actually convert this back to the time domain if we want to. And in the time domain, then this will be omega t. And on the right-hand side, then we will have the convolution of the time domain version of this with the electric field. Okay. So the electric field is, sorry, this should be a function of time. Okay. In the time domain, a product becomes a convolution. We have a product here. But in the time domain, it becomes a convolution. But things are very simple. In the time, in the frequency domain, we just have to deal with products. And in general, we can use this kind of relationship in a linear time invariant system. So we're going to assume LTI systems, so that a product in the frequency domain just becomes a convolution in the time domain. That actually simplifies our analysis a lot more. And we can look at the general case to gain more insight. So P in the frequency domain is very simple. It will be in general given by epsilon naught times chi. This thing is read chi in the Greek letter, times the electric field at that position as a function of omega. Then d of r of omega then would be equal to epsilon naught e r of omega plus chi times epsilon naught r of omega e of r of omega, because we have used the formula that d is equal to epsilon naught e plus p. Okay, we'll just use this formula. And if you rewrite this formula, you can see that I can actually define a new constant here. Let me not write the details out in full. Okay, I can call this my effective permittivity. And this hence can be written as something like epsilon, which could be a function of r and omega times e times r of omega. Okay, so this makes things very simple. Whatever we have learned previously, the only thing that we need to change is to make this epsilon as a function of frequency. This can be thought of as a transfer function in our linear time invariant system. The input is E, and then this is our output. Okay, so this essentially is an LTI system, okay? And oftentimes we would just drop the R and just say that epsilon is a function of frequency. And when epsilon is a function of frequency, we say that the medium is frequency dispersive. Okay, the medium is frequency dispersive. However, if epsilon is a function of position, R here stands for position. It is a position vector. Okay, it means that it's inhomogeneous dispersive medium.
I have a question, Professor.
Oh, sure, sure.
Which dimensions do you consider for this epsilon for effective permittivity? Is it tensor or just a scalar for now?
It's a scalar at this point. Tensor is too complicated. You're thinking ahead, okay? It's just a scalar relationship now because we say that D is epsilon E. This is vector. This is vector. This is a scalar. Okay, so it's a simpler relationship. Good that you asked this question, okay, because we can generalize it to other kinds of medium. By the way, just before I forget, this medium is also called a heterogeneous medium. Okay, heterogeneous medium. Okay, any questions so far before we move on to the tensor case? Okay, as Ivan has pointed out, you can actually go to the tensor case and say that the relationship does not have to be that simple. The relationship that we had assumed before is that the polarization density is just epsilon naught chi times E. Okay, but we can generalize it to the case where the polarization current is given by epsilon naught times chi times E. Okay, what is the tensor? Chi is called a tensor. So what is a tensor? Let's stop a little while to think about what a tensor is. A tensor is something that maps a vector to another vector. So you can think linear algebra in this. if you have a course in linear algebra, okay, you can think of this as being a P is the 3 by 1 vector, column vector. And then chi is a 3 by 3 matrix. Okay, and then dotted with E again, which is again a 3 by 1 vector. So the concept is no different from linear algebra, as that the chi is replaced with a double bar, which means that it is a matrix now. But in the language of physics and electrical engineering, when a matrix relates two vectors, okay, when you have a 3 by 3 matrix that relates two vectors, those matrices are called tensor. It's just a nomenclature that if you have a 3 by 3 matrix, it's called a tensor. So all tensors can be thought of as matrices, but not all matrices are tensors. Okay, so you can think of a tensor being a subset of matrices. Okay, it's a subset of matrices. Then what are the example of a tensor? We can take the example of this idea, and this idea means that I can now write D as being equal to epsilon E plus epsilon chi dot E, and then I can write this as 1 plus chi dot E. Okay, where I just have factor out the E. This by right should be an identity. Should by right be an identity tensor or matrix. Okay, tensor and matrix are the same, but usually people just write 1. They don't bother to write it as the identity. If you want, you can be more elaborate and write this as identity tensor. Okay, but usually people are sloppy, they just write 1 there. Okay, then what I have is that I can write this as the matrix times an E. Okay, now this is called a tensor or a permittivity tensor. Okay, this is called a permittivity tensor. What are examples of a tensor? Well, the difference between a scalar and a tensor is that in the scalar, D and E points in the same direction. Let's assume that epsilon is a very simple tensor. Be epsilon naught, epsilon 2, epsilon 3, 0, 0, 0. So it's a 3 by 3 matrix. So what it means is that when they apply this on an electric field, the epsilon dot E would be equal to epsilon 1 EX plus epsilon 2 EY plus epsilon 3 EZ, and this would be your electric field. Sorry, I should have X component here. I should have a Y component here. I should have a Z component here. You can see that in this picture, D and E do not point in the same direction. That is, if I have an electric field E pointing in this direction, then epsilon dot E may not point in the same direction as E, because these 3 coefficients can be different. Okay, epsilon dot with E does not necessarily point in the same direction as E, but then your D points in this direction. So D and E do not point in the same direction. There's a peculiarity about tensors. Can everybody see that? Or you need more clarification? Okay, this is a very simple tensor. You can see the physics quite easily. But you can generalize it to matrices that are 3 by 3. And when we have epsilon 1 not equal to epsilon 2 not equal to epsilon 3, we call this a biaxial medium. And when epsilon 1 equals epsilon 2 not equal to epsilon 3, this is called a uniaxial medium. Okay, so So any questions so far? If not, then let's move on to the next topic, which is that the fact that so P in the frequency domain is just equal to epsilon naught chi chi of R omega E of R omega. And if you were to write this in the time domain, okay, this would be rather complicated. Then it would just become P R T will be equal to, if I write out the convolution in full, okay, then it will look something like this. dt prime chi of R t minus t prime times E of R t minus t, sorry, t prime here, should be just t prime. Okay, this is what the convolution is. Okay, you probably have learned about this in your undergraduate course. Okay, so we know that all linear systems can be written in such a manner because in the undergraduate course, if you have an input x1t, and if the output is y1t, and then if you have the same system that you have x2t, and then output is y2t, and then we know that now if you put the two inputs together, the same system, you have maybe a linear superposition of these two inputs. Okay, what do you think would the output be if you have your undergraduate course before that defines what the linear system is? What do you think is the output now? Anybody wants to volunteer?
It should be A1 Y1 plus A2 Y2.
Very good. That is what we learn as good electrical engineers, that this would be A1 Y1T plus A2 Y2T. Okay, this concept can be generalized to a more complex case where you have a convolution of both space and time. Okay, you can actually define a kind of relationship where this thing, let's take the Fourier transform in space. Let's take a Fourier transform in space. Then if we can write something in this manner, okay, where we define P of K omega to be just a Fourier transform in space of P of R omega e to the I it went away. Okay. Oh, this thing is very sensitive. Let me make it small. Okay, then you will have something that looks like, say we do a Fourier transform in 3D space. You get this, you know what I mean, okay? If you, for those of you who have studied more advanced Fourier transform technique, okay, then this will give rise to a convolution in both space and time. And I discussed this in the lecture notes. And when you have this kind of thing, then chi, k of omega, is spatially dispersive as well as frequency dispersive. You don't have to know this concept in this course. I just want to generalize it so that you know that this kind of concept can be generalized to a spatial dispersive medium as well as frequency dispersive medium. Okay, so that is what frequency dispersion is, and then we can have concepts like an isotropic medium. Okay, by the way, something that behaves like this, we also gives it a name of anisotropy, which means that the electric field and the electric flux do not point in the same direction. And you can generalize this to by an isotropic medium. In that case, you would say that D would be epsilon dot E. The electric flux is proportional to electric field, but there is also a possibility that this is I call C dot H. There is also a possibility of a contribution to the electric flux from the magnetic field. By the same token, you can also have a case where the magnetic field contributes to the magnetic flux, and then you can have the electric field contributing to the magnetic flux. This thing is pronounced zeta, I think. This thing, I think, is pronounced Kasi. Kasi. I think this is how we pronounce it. I'm not sure. Okay, Kasi. So then we also have the case of nonlinear media. In the case of a nonlinear media, instead of having P being just linearly proportional to E, and you can actually test linearity quite easily. So you can easily show that if I input E1, I get P1 as my output. If I input E2, I get P2 as my output. And then I can test the case that if I put the linear superposition of 2E1 plus alpha 2E2, then you can show that the output is alpha 1 P1 plus alpha 2 P2. So this is a test of linearity. You can plug this into this equation and show that this is true. And hence this describes a linear medium. However, if I have a case where P is epsilon naught chi, but the chi itself depends on the input E. Okay? And if that is the case, the test of linearity would have failed. If you go through this test, you will show that this is not true anymore. This kind of medium is called a nonlinear medium. Okay? And then this kind of medium is usually encountered in optics as well as low frequency electrical engineering. The place where you would encounter this in optics is called a Kerr medium or Kerr effect. And in the case of electrical engineering, especially in the power engineering field, okay, we do power engineering. Then you can have B ordinarily will be just that, but you can have a case where the flux, magnetic flux B is dependent on a mu that is a function of H dot with H. And then what you have is something very interesting. If you were to plot B and H, it would not be a straight line. It will not be a straight line, but it might go something like this, that it go like this. And if you change the direction of You probably have seen this in your undergraduate course. So if you increase magnetic field, the B flux would go backward in this direction, and this is called a hysteresis loop. Okay, and this is very important in power engineering. You can show that the area under the hysteresis loop is the power loss. Okay, any questions before we move on? Well, if no questions, then let's look at wave phenomenon in the frequency domain. Okay, we have seen the wave phenomenon in free space, in vacuum. But then we show that when we have material media, we can describe the material media with an epsilon, which is just something like this. Okay, and this can be very complicated because my chi can be a function of frequency, and it's very complicated to take this relationship back to the time domain, because then D is just a product in the frequency domain. And I don't like to take it back to the time domain, because then in the time domain, this would be a epsilon t convolving with E of t. This is too complicated. I don't want to deal with convolution. I like to deal with simple products. So why don't I just look at Maxwell's equations in the frequency domain? And that would make life a lot simpler for me. And so we have Maxwell's equations in the frequency domain, and it will be given by curl of H. Sorry, let me start with Faraday's law. Curl of E, okay, is equal to J omega mu naught H. And then curl of H is J omega epsilon naught E. And let's assume that there's no source, because we want to study just with phenomena with no source. But when we want to include material media, it's very easy to do so in the frequency domain. We just replace it with effective epsilon. So in the frequency domain, Faraday's law or Ampere's law becomes very simple. Ampere's law just becomes J omega. At first it was epsilon E plus P, but then we say that P is equal to chi E, and then we can just replace this with just an epsilon effective. Okay, so there's no difference whether you include material media or you do not include them. The two are of the same structure mathematically. So let's see what we can do with this equation in the frequency domain. Let's take the curl of the first equation. Let's take the curl of the first of Maxwell's equations. Then on the left-hand side, we will have curl of E. Okay, this actually is a quantity in the frequency domain. I usually don't bother to write it down. And then I would have curl of H in the frequency domain. And most of the time, we don't bother to write this nitty-gritty detail down. And then I can take the second equation, Ampere's law, and replace that with that. Okay. Then if I do that, then the second equation becomes minus omega squared mu naught epsilon. This is the effective epsilon now. Okay, E. Okay. And then what I have now is that I can simplify the left-hand side. How would I simplify curl of E? Anybody? If I have a double curl of E, what identity do I use to simplify this double curl?
It's called back of the cat.
Very good. The back of the cat formula. One thing to notice is that this is implied, but this actually means this. Okay, this is implied. We actually take the curl of the first thing, and then if we apply the back of the cat formula, this would be the same as this. you have to apply that in the right order so that the function is always to the right of the del operator. And then we can write this as the Laplacian of E, okay? And we can assume that the medium is source-free. J is equal to 0. So charge is equal to 0, okay, because we know the divergence of J is d rho dt. And in the frequency domain, it's just J omega rho, okay? Since J is 0, rho is equal to 0. So rho is equal to 0, divergence of E is equal to rho, and then it should be 0. Since there are no sources in this space that we're talking about, then I can simplify the left-hand side and end up with an equation that only involves this term. And then I can collect terms and obtain the fact that Laplacian plus omega square mu naught epsilon times E is equal to 0. Okay, is equal to 0. Remember that this epsilon now is the effective epsilon. Is epsilon that incorporates the polarization current. Okay, and let's study this equation in greater detail. Okay, we can actually write this equation in such a way that we call this k naught square, which is omega square mu naught epsilon, which could be a function of frequency. Okay, and then this is equal to omega square over v squared. Okay, where v now is something that is different from what we know before. It will be given by 1 over square root of mu naught epsilon. Okay, so whatever analysis we did before, we find a new velocity which is given by this. Okay, so let's simplify our life and make things simple. And assume that we have a very simple problem to solve, that the electric field is pointing only in the x direction, and then it only has an x component, and it also is a function of z only. Okay, it's only a function of z. So there's no x variation, there's no y variation. Okay, so the Laplacian then that we have in the previous equation just becomes partial square, partial z squared. Okay, so if we go back to this equation that we have derived, this equation is also called the Helmholtz wave equation, or the Helmholtz equation. Okay, Helmholtz equation. And if we go back and look at the Helmholtz wave equation, the equation, it simplifies to something rather simple. And hopefully all of us know how to solve that. And I can write this as partial square, partial z squared. The Laplacian just becomes that. And then I can write this as k naught squared. Okay, so I can write Helmholtz equation as just this. And then the E has only an x component. Okay, I just would have that. And this is an ODE now, actually. This is just the same as this. Instead of a PDE, this is called ODE, which stands for ordinary differential equation. Okay, and all of us have solved ODEs, ordinary differential equations, a lot in our undergraduate course. And what are the solutions of this ODEs? Does anybody know or want to volunteer for the solution? So remember that all these are in the frequency domain only, even though it's a function of z, it's actually also a function of frequency. Okay, what are the general solutions for EX to this ODE? Does anybody want to volunteer?
It's a linear superposition of exponentials.
Very good, Ivan. It's a linear superposition exponential. I can write it as two terms. Okay, you can plug this in and convince yourself that this is the general solution to this equation. Okay, these are exponentials. You know that, let me draw a line here so it's not confused you. We know that when we have a second order ODE, we have to look for two solutions. If you have a first order ODE, there should only be one solution. So since this is a second order ODE, the second derivative, we have to look for two solutions. And these two linear superposition are the general solutions that we have. And remember that we are doing all these things in the frequency domain. And if you want to look for the quantities, these quantities in the time domain, you remember what we have to do? These are frequencies in the frequency domain. And using phasor technique, we know how to go back and forth between time domain and frequency domain. What do we have to do to get the time domain solution? Anybody?
Inverse Fourier transform.
Inverse Fourier transform is a rich man's way of doing this. Say if you have not learned Fourier transform before, what is the poor man's way of doing this? Assume that your knowledge is not very rich. You haven't taken many advanced mathematics course, but you have learned phasor technique in electrical engineering. How would you obtain the time domain solution of this problem? What do you do? Anybody?
Use the sine function for...
Sine function is true, it's sinusoidal. The solution in a time domain has to be sinusoidal. That's how phasor techniques come about. We assume that the solution is time harmonic or sinusoidal. And then we do back and forth between time domain and frequency domain. So we have to learn this as good electrical engineers, how to go back and forth between frequency domain and time domain. Using Fourier transform is a rich man's way of doing it. But if you do not know Fourier transform, how do you get back the solution in a time domain?
Using okay, you're fine. We just multiplied by the exponential j omega t and then take the real part of this.
Yes, very good. That's a poor man's way of doing that. Okay, very good, Ivan. So you have this in the frequency domain. This is usually a complex number. Okay, even though I didn't bother to indicate it. Then you multiply by the time dependence that you have assumed to go back and forth. And then you can obtain the time domain solution and the frequency domain solution very easily. So let's make things simpler. Okay, let's make things simpler so that we can study the physics more easily. So K naught square can be omega squared mu naught epsilon. Let's assume that epsilon is just equal to epsilon naught to make things simpler. So K naught squared is just omega squared mu naught epsilon naught. So we go back to the vacuum case where there's no material present. Okay, and then we look at the Helmholtz wave equation again. Okay, we look at Helmholtz wave equation again. Then we say that we have this vector wave equation for the electric field, which was shown to be equal to this in general. And then we can use the identity and rewrite this as Laplacian of E minus omega square mu epsilon E is equal to 0. And then let's assume that since there are so many derivatives here, remember your Laplacian is just equal to this. It's just equal to that. Let's assume and be clever and have the hindsight that the electric field as a function of R would be something that is a constant. Okay, this is a constant vector. And then the only space dependence that it has is this very simple space dependence, like exponential functions. So let's assume that it is very simple like this, okay? Then these functions are very simple because when you operate this with this Laplacian, if you were to differentiate with respect to x, you just bring this thing down 2 times. So partial x squared becomes minus kx squared. Partial y squared becomes minus ky squared. And then partial z squared becomes minus kz squared. So now if I plug this into this equation, okay, make use of all these nice properties because they're the very simple exponential functions. The Laplacian is this, and when they operate on this function, it becomes very simple. Then the Helmholtz wave equation, just becomes something very simple. The Laplacian becomes minus kx squared, minus ky squared, minus kz squared. And then the Helmholtz wave equation just becomes minus kx squared plus ky squared plus kz squared. Okay, E, I can still put this E as itself, and then plus omega squared mu epsilon E is equal to 0. Okay, and in order for this equation to be satisfied, and I can see that kx squared plus ky squared plus kz squared has to be omega squared mu epsilon. Okay, this is called the dispersion relation in wave theory. And you can think of kx, ky, kz as variables. Okay, you can think of it as in mathematics. Of course, when you take a math course, they won't use kx, ky, and kz as a variable. Most likely they're not. In your math course, they will give you an equation like this. Okay, what is this equation of? What kind of shape does this have? This is an equation of a what?
Should be a sphere.
Anybody? A sphere, very good. It's an equation of a sphere. So this is the equation of the sphere in the kx, ky, and kz space. Okay, think of this. It says that they are vectors. Okay, the vectors are given by kx, ky, kz, and that kx, ky, kz makes a sphere. So I can think of a k vector as being consisting of x component, y component, and z component like this. And then that k vector would have a constant length, and its length will be given by this. This is very much like the equation of a circle. If you go back and revise your geometry or your undergraduate knowledge, that you are going to have a vector which is called a position vector. Okay, this should be y. Okay, and then the equation of a circle gives this, and by the same token, you get the equation of a circle to be that. And then this circle, this sphere is also called the Ewald sphere. Okay, Ewald sphere. So there's something very interesting which says that if you assume an equation of this very simple form, okay, given by this thing over here, this simple form actually satisfies this Helmholtz wave equation, but this is very long to write. Okay, I'm going to use a shorthand notation and say that if I define the vector k to be this, and then a position vector r to be this, k dot r is just equal to kxx plus kyy plus kzz. Agree? everybody knows how to take a dot product between these two vectors. So instead of writing it in the long form, like this manner, okay, instead of writing it in the long form, okay, I write this 3 exponential, okay, into one exponential. And if you use your knowledge of exponential, it can be summed into 1 in the exponent. And then this can be written as e to the minus j k dot r. Agree? So this is called the equation of a plane wave. And since this plane wave does not decay or vanish in amplitude in any way, this is called a uniform plane wave. You can show that if you have E, a position of R is given by E naught e to the minus j k dot r, which is our shorthand notation for writing this very complicated expression, okay? You can show quite easily that, let me see. You can show quite easily that if I were to take the magnitude of this, and do you know how to take the magnitude of a complex vector? Okay, the magnitude of a complex vector square, this is complex number, so it has to be taken in this manner. Okay, it has to be taken in this manner. You can go back and revise your complex algebra. Okay, the magnitude of a complex vector is taken to be that. And you show that when you plug this into here, its magnitude is always E naught squared. Okay, that's why it's called a uniform plane wave. Its amplitude does not change with respect to position. Okay, this is true for all x, y, and z. This is a mathematical symbol for all. Okay, so this is one thing you notice about uniform plane waves. They don't change in magnitude. There's another very interesting things about uniform plane wave. If you think of it as being R, okay, is something like this, and this is your E. And if you were to pick a plane in a 3D space, and for simplicity, we just look at the 2D space. We pick the position vector R. Okay, this position vector R is x plus y. And then if you pick it such that k vector, k is now a position, a wave vector, we call it a wave vector. If you pick these two vectors such that the k dot r is always a constant. And can you see that on this surface, or this plane, k dot r is always the same. No matter where r is, you can pick r on any points on this surface. K is fixed k, and then change your r. And if you take the position vector and dot with k, it depends on the cosine of that angle. But then it's just the k component of this position vector r. So k dot r is always a constant. So if you make k dot r a constant, then this phase, this thing in the exponent is always a constant along this plane. So I can take other planes. I can take another plane here, pick another constant, another constant, another constant, another constant. This thing will be constant phase along all these planes. Okay, you can see that this is very interesting because it says that the phase is a constant along all these directions. And the phase being a constant means that if you were to translate back to the time domain, it says that along along this plane, the wave has a constant phase, okay? And this is the characteristic of a plane wave. That's why we call this a plane wave front. So this is beautiful because it gives you a picture of what the plane wave is. In addition, if you go back to the analysis and look at this again, okay, this is your plane wave. You're assuming that the plane wave is something of this form. And there's something that I won't show in great detail, but essentially what we say is that if you assume that ER is a constant times e to the minus jk dot r, okay? If you plug into Maxwell's equations, curl of E, according to Faraday's law, will be equal to that. And then if you plug this in here, curl of E is x partial x plus y partial y plus z partial z cross with E. Okay, you can plug it back in. Okay, and then you will see that this will just become, because of the simple behavior in the exponent, this will just become kx. Let me put a j somewhere. There should be a j somewhere. Okay, minus xjx plus minus y hat jky minus z hat jkz cross with E. Can you see that this derivatives, when operating in this function is very simple. It just becomes something that looks like this. Okay, that function in detail is something that looks like this, and when you differentiate it with respect to x, y, z, you just bring all these components down in this very simplified form. And so what you have is that the Faraday's law just says that, if I look at Faraday's law now, it has a j, it just said that j k cross E is equal to minus j omega mu not h. Okay, there was no something not there. So what it says is that k is orthogonal to E. Okay, that I haven't proved, but what it says is that k cross E is minus omega mu naught h. Okay, another thing that you can say is that divergence of E equal to 0, and you plug this in here, and it just means that jk dot E is equal to 0. Again, for the same reason that the del operator just becomes this. And if you plug in the del operator, it just becomes jk dot E, and then k dot E equal to 0. What it says is that k is orthogonal to E. Okay, k is orthogonal to E. So if you look at the k vector, okay, this is called a k vector. If you draw in space, it has to be orthogonal to E because of this condition. And then k cross E has to be pointing in the direction of h or minus h. So if you take k and cross with the E, okay, it points in the direction of E. Let me see, do I get it right? K cross E. Now k cross E is minus h. Okay, so h must be pointing into the paper then. Okay, did I make a sign error anywhere? I hope not. Okay, so K, E, and H make an orthogonal system. This is the right-handed coordinate system of E cross H. You can also see that E cross H points in the direction of K. So this is the characteristic of a uniform plane wave. You can show other things, which I'm not going to show, that the H and the magnitude of E is shown in the lecture note. Okay, this is a constant that is equal to like current over voltage. Current over voltage should be square root of epsilon over mu. Epsilon over mu. Okay, it should be having this ratio. You can show this also, which I show in the lecture notes. Okay, so I will stop here. Not stopping the lecture. I will move on to the next lecture and talk about some other things. You can read about the detail of this in the lecture notes. Okay. What I want to talk next is actually on lossy medium. I want to talk about lossy medium, and then we like to talk about this in the context of Ampere's law. We say that in Ampere's law, we have this thing, and this can include both epsilon naught E plus P. We can say that they can always be written in just one aggregate term, but if we have a lossy medium, there is a J in Ampere's law, but if the J is coming from conduction current, we can write that as such, okay? You can see that in the frequency domain, things actually becomes very simple. The right-hand side then can be written as J omega epsilon, which includes all kinds of material properties that can vary in P, plus the fact that the second term, I can write it as minus J sigma over omega E. Okay, I can write it as such. Okay, I can just combine the two, and then I can write it as plus J omega epsilon under tilde times E. You can see how powerful this is. Ampere's law with displacement current plus polarization current plus conduction current, all three of them can be embedded into this complex permittivity. This is called the complex permittivity. Okay, so this is no different from Ampere's law in free space, except that epsilon naught in free space or vacuum get replaced with epsilon tilde. Mathematically, the two equations are homomorphic. I use the term homomorphism because they look so for free space or vacuum, you can apply the same math that you have done for conductive medium. Okay, this is lossy conductive medium. So we learned how to solve Maxwell's equations when this was epsilon or epsilon naught, but now that you have a complex permittivity, the same mathematical analysis applies. So you can get the wave equation as we did before, then you will have just omega squared mu naught. But now the epsilon here will be a complex permittivity. We can no more source because J external is equal to 0. You will get an equation something like this if you go through the math. And then again, with the same argument, you can see that E has to be something of this form. Beautiful, okay? Whatever I did before, I can reapply my knowledge. And then the K, again, is a vector with 3 components, as I had before. But there's one catch here. The catch here being that the dispersion relationship that I have derived previously is now this one. Previously for this free space case, or for the non-conductive medium case, I show this to be true. We plug this into that medium, and then after we plug that in, we show that this has to be true. Okay, we show that this has to be true. Equation of a sphere. Okay, except that epsilon is not the complex number. But now you go through lossy medium case, what you have to do is the same equation applies. You just replace epsilon with a complex permittivity. Just the same algebra applies. The equations are homomorphic to each other. Okay, so again we have divergence of. We can show that divergence epsilon E is equal to 0 because you can take the divergence of this equation. Okay, you can take the divergence of this equation and get this equation, which is the third equation in Maxwell's equations. Okay, this equation applies, and then you still have a very nice relationship. This is still called the dispersion relationship. Okay, except that epsilon can be complex, and that gives rise to some very interesting physics. Okay, let's look at the case of a conductive medium in greater detail. And then what we have then is that epsilon is epsilon minus j sigma over omega, which is what we did before. We say that if we define a new complex permittivity given by this expression, then your wave number, the wave number that you get, say if you assume that E, you can still plug this in as we did before for a plane wave and look at the solution. The solution still has to be something of this form, is 1D, except that K would be that of a square root of this function. You can still put mu naught here if you want to, but this is a complex number now. And then if you look at this in greater detail, it's epsilon minus j sigma over omega. And when sigma is much, much larger than omega epsilon, or the same as saying that sigma over omega is much, much larger than epsilon. If this term is much larger than that term, then this is essentially equal to omega mu naught j sigma over omega. Okay, and all of us know how to take the square root of j. Square root of j is square root of e to the let's say a j pi over 2 is e to the j pi over 4, and this actually gives you something like 1 over root 2 1 minus j, or 1 plus j. Yeah, 1 plus j. Okay, you can take the square root of this, and that is what you get. And you can show that if you take the square root of that, and k will have two parts. Okay, it will have a real part and then an imaginary part. Okay, we have something like this, and you can show that the imaginary part and the real part are almost equal to each other if you have a conductive medium where this is true. This is just a statement that conduction current is much, much larger than the displacement current. Okay, and then the wave would decay exponentially in the z direction. If you plug this number in here, e to the minus jk z will consist of two terms, e to the minus jk prime z, e to the minus k double prime z. And then the wave decays really fast. And then you can show that, I show in the lecture note that k is the square root of minus j omega mu sigma. Okay, if you were to just take the square root of this, combine the omega together, you will find that k is equal to that, and then it is equal to 1 minus j omega mu sigma over 2. Okay, so you can calculate that k double prime quite easily. It's given by omega mu sigma over 2. Okay, and this is the decay length. Okay, if the function decays like this, then z is decaying to 1 over e in this length, and this decay length is known as a skin depth. Okay, skin depth is just the reciprocal is equal to 2 over omega mu sigma. This formula is very important. It says that decay length of a wave in the conductive medium is given by this. This is very important for submarine communication. In order for you to talk to the submarine, the ocean is the lossy medium, because in the ocean, if you compare these two terms, okay, omega epsilon is much, much less than sigma, which means that displacement current, this is displacement current, this is conduction current, okay? That if you are in the ocean bottom, you're essentially in an environment where the medium is conductive. And in order for you to talk to a submarine, you want to make the penetration depth as large as you can. So the conductivity of the ocean, you cannot control. But there's one thing you can control, which is to make the frequency very low. So in order to talk to the submarine, you can use very, very low frequency signal. Okay, you can use very, very low frequency signal. But what is the problem with working with very low frequency signal? Does anybody know? If you have to talk to your buddy who is in the submarine and you need to talk to him, you find that the ocean clears and everything in the ocean will decay in this. It says my internet connection is not stable. Is that the case? Okay, can you hear me? Hello?
Yeah.
Okay, it said that my internet connection was not stable. So I just hope that it's stable now. So what happens is that things decay very, very rapidly. And in order to talk to your buddy, what can you do with this formula to increase the penetration depth of your electromagnetic signal? What else can you change in your radio communication device? You have to operate it at very low frequency. And what is the problem if you operate the communication equipment at very low frequency? What is the first problem that you have?
You'll need a large antenna.
Does anybody? You need a large antenna, which is true. And all the submarines usually drag a very long piece of wire behind their back. Use that as the antenna. What is the second thing that comes to your mind when you have to operate the communication system at very low frequency? These frequencies are called BLF or ULF, which stands for very low frequency or ultra low frequency communication. What is the second thing that comes to your mind?
Low data rate. Low
data rate, which is true. Well, very good, okay. Say if you want to send zeros and ones, okay, you can send zeros and one with the carrier frequency. And what is done now is that you have to use this to modulate on top of a carrier. There's one way you can send it. Okay, so if your carrier has very low frequency, say if you work in kilohertz range, your ones and zeros have to be far apart in order to be carried by the carrier. So your data rate is very low, okay? So there's another thing that comes to your mind when you have to talk to your buddy in the ocean floor Okay. I hope you don't have to talk to them. Okay, but that's the case. And so that is the case of a conductive medium. But what happens is that this complex permittivity is given by this formula, which we can write it as epsilon 1 minus j sigma over omega epsilon. And what happens if you are in the other extreme where omega epsilon is much, much larger than sigma? If you look at Maxwell's equation on the right-hand side, you have curl of H is equal to j omega epsilon E minus plus sigma E. Okay, so this is displacement current, this is conduction current. So if you're at the other extreme where the displacement current is much, much larger than the conduction current, then you can make approximations where you've assumed that K is still given by this formula. This formula is still true because mathematically it's still valid. The algebra is still the same, except that now you will have to replace this with j sigma over omega. Okay, so if the second term is small compared to the first term, you can make approximations. You can make approximations that this is omega mu epsilon 1 minus j sigma omega epsilon to the half. So you have something where this is small, this term is small. So if you have something like 1 plus x to the half, and if x is very small, what is this approximately equal to? It's something that we do in freshman mathematics or high school mathematics quite a bit. How can we approximate this function? Square root of 1 plus a small number. What is it approximately equal to? Anybody? One plus x to the half, to the power of half. Or maybe I ask you a more.
1 plus x.
What?
Should be 1 plus x.
No. Let me ask you another question. What is 1 plus x to the power of n if x is very small?
1 plus nx.
1 plus nx, very good. 1 plus nx. You can get this either by binomial expansion. You can also get there by using Taylor series expansion. Okay, if you do a Taylor series expansion, you get the same formula. So this formula is just 1 plus half x. And you can use that to approximate this thing that you have. And then you have the other case where you have a medium where displacement current much, much larger than conduction current. Okay, in that case, you're not at the bottom of an ocean floor anymore. You are some kind of medium where you're designing some electronic circuits where conduction current is not a nuisance, but they're due to lossy things around. And then you will have to make this kind of approximation. I'll stop here. Are there any questions before we stop here? Well, if there are no questions, then I should stop here and let you go. Okay, we'll see you on Thursday then. Okay. I'm thinking of having an office hour at 8 p.m. tomorrow night because I have some online students and they're in the West Coast, like California. There's one even in China. And most of the students are in the Midwest or the East Coast. So I'm thinking of having an office tomorrow at 8 p.m., but I can hold one today too at 3 p.m. if you have any questions regarding the course. Okay? I'll let you go and talk to you later then.